All right, hello everyone. This is part 2 of chapter 6, viscous flow in ducts. In part 1, we started with the introduction to viscous flow in ducts. We talked about the laminar flow, turbulent flow transition. We also talked about the velocity profiles in laminar flow and turbulent flow. We discussed the entrance length, and we said that at the beginning of the at the beginning of the flow into a pipe or duct, the flow is still developing, but after a while the flow becomes fully developed. So now in this chapter we are going to continue and develop equations in order to be able to go ahead and calculate the head loss in a duct flow. And this is the acknowledgement slide as usual, so I'm not gonna go over it again. Okay, so let's consider a segment of a pipe. It's a general case and it is therefore inclined. So in order to consider the effect of a change in the elevation at section 1, so let me activate my pen here. All right, so at section 1 the pressure reading is P1, and at section 2 it's P2, and P1 is equal to P2 plus a delta P. So pressure in section 1 is higher as expected. We do have the gravity vector. It's vertical, and the component of the gravity in the direction of the pipe in x direction is g sine phi, which phi is the inclination angle here. The length of this section is x2 minus x1 equal to L, and in terms of z, the vertical change in the elevation, delta z is equal to L sine theta. All right. So it's a laminar flow, so we want to find the friction factor and head loss because of friction first for laminar flow, and then we will go ahead and find it for turbulent flow. For laminar flow, because there is an analytical solution available as discussed in chapter 4, therefore it's straightforward. We can find it, it's not 100% analytical, but it is at least it's semi-empirical. Okay, and the velocity profile is parabolic. Here it looks kind of circular, but it should be parabolic. Okay, all right. So first let's start with the continuity equation. Q1 is equal to Q2. The cross-sectional area is also constant. Therefore, V1 is equal to V2 equal to V, the velocity. The velocity is the same in every section of this tube with the constant cross-sectional area. If we write the energy equation between section 1 and section 2, 1 being this section and 2 being the other section of the pipe. So this is the energy equation, or sometimes it's also called the modified Bernoulli's equation. P1 over gamma plus V1 square over 2G plus Z1 equal to P2 over gamma V2 square over 2G plus Z2 plus HF, which is a head loss. So the head loss, like in previous chapters, it was like given. We were told that okay, head loss is equal to, let's say, 5 meters. But now in this chapter we want to see how to actually calculate this head loss. So that's the purpose of this section. So if we put velocity V1 equal to V2, so this term will cancel out, the velocity term will cancel out, and we will end up with this equation HF, the head loss or friction loss is equal to Z1 minus Z2 or delta Z plus a difference in the pressure divided by rho G. So because this tube is not horizontal, so HF is not only due to delta P, it is also because of delta Z. So we need to take this into consideration, and the energy equation directly provides that. Now we go ahead and write the momentum equation along the x direction. The momentum equation was the subject of chapter 3, momentum equation in a control volume. Now our control volume would be this segment of the pipe from section 1 to section 2. It also includes the walls. So around the walls we do have shear stress, and inside the control volume we do have a pressure change at the beginning and at the end. We do have a shear force acting on the control volume from the wall acting on the control volume, and we do have a body force acting on the control volume, and that body force is the weight of the fluid inside this control volume. So if we write the momentum equation along the x-axis, which is the axis of our interest, the sum of all forces acting on this control volume is equal to the rate of change of the momentum. So the rate of change of the momentum, so we see that that's equal to m dot v2 minus v1 in the same direction, and since v1 is equal to v2, therefore the momentum coming in and going out is equal to 0. So what remains is the sum of all of the forces acting on this control volume. So we do have pressure acting here on this direction, so this pressure, and also a pressure force, actually a force. If you multiply the pressure by the area, it gives us the force. So a force on one side and another force on the other side. So the net force is delta P across these two cross sections multiplied by the cross-sectional area of the pipe, which is pi r squared. So the first term is the pressure force, which is like the pressure force acting on this tube. It's like pushing the control volume, which we have defined inside this tube. Then the next term is the weight of water or liquid, fluid, or gas inside this control volume. The weight is simply mg. So what is the weight of this in the x direction? So m is rho multiplied by the volume. Volume is cross-sectional area, pi r squared, multiplied by the length, like L, and then multiplied by G, and then we do need another sign phi because it's only in the direction of x. So that's the force. So that's the component of the weight, which is mg in this direction. So it becomes like mg sine phi. So that's the component of the weight in the x direction. So it's the second term is simply mg multiplied by sine theta, the component of the weight in x direction. And then the last term here is the force acting on the control volume because of the shear stresses acting on the walls. So the shear stress therefore multiplied by the perimeter of the cylinder, which is 2 pi r, the perimeter of the circle multiplied by L, so the total perimeter of the cylinder, multiplied by tau gives us the shear force acting in the opposite direction, upward. So pressure force is acting downward, weight in X direction is acting downward, and it's balanced by the shear force which is acting upward. So if we divide all of these terms by pi r squared and also divide by rho g, we will end up with this equation at the bottom. Delta z, which is L sine theta. L sine theta in this equation is equal to delta z. And we have divided them by pi r squared and rho g. So what remains is L sine theta, which is delta z. And then for delta p, it becomes delta p over rho g. It is equal to the tau term, which is this term that you see here. So that's the tau term divided by pi r squared and also rho g. So we end up with this equation here. So from here to here, we change r to d, the diameter, because usually in tubes, the head loss is expressed in terms of the diameter rather than radius. So as a result, delta p over rho g plus delta z is equal to 4 tau wall divided by rho g times L over d. So that's what we get from the momentum equation. But what is this HF here? Well, this HF actually comes from the energy equation that we have up here, because delta Z plus delta P over rho G is equal to HF. So we can bring HF here as well. In other words, the head loss HF that we want to formulate from one hand is equal to delta Z plus delta P over rho G. And on the other hand, it's equal to, is related to tau on the wall and some, geometrical parameters and the rho g term. So this is a very important equation, and we are going to use it in order to develop an equation for the head loss. All right, so what we obtained in the previous slide, we found this relationship between delta z plus delta p over rho g, which is equal to the head loss, and it is related to the shear stress on the wall surfaces. In 1850, a German professor Weisbach, in a series of experiments in pipe flow, he observed that actually the head loss is proportional to the length of the tube or its diameter and square of the velocity. Then he proposed that we go ahead and therefore, based on the observations, we show HF, the head loss, as a function of L over D and also velocity squared, and then make it dimensionless by using G and also a factor F. Well, factor F is actually dimensionless, so which is called the friction or Darcy friction factor. So this F is the Darcy friction factor, which is dimensionless and we need to find. And HF has unit of length as we had before, but this F is dimensionless. So it means that the unit of the other two terms is the same as the unit of length, which is of course the case because L over D is also dimensionless, and V squared over 2G as the unit of length, as we understand from the Bernoulli's equation. So now we do have this empirical equation for HF, and we do have this analytical expression for HF in a laminar flow. So if we put them equal to one another, so we can actually find this relationship between F, the Darcy friction factor, and tau, the shear stress. And the next step is to go ahead and look up the equation that we derived before for tau, the shear stress on the wall, that we developed before in chapter 4 for laminar flow in a pipe flow. All right, so in general, this factor F in a pipe is a function of the Reynolds number based on a dimensional analysis. The duct roughness non-dimensionalized with respect to the diameter is a duct roughness. The surface walls of the duct, the inner surfaces of the wall, they do have a roughness. It is very small. We cannot see it, by naked eye, but there is a roughness. So like the surface of the glass, which is very smooth, if you compare it with the surface of, for instance, a carpet, which is kind of rough. So the inner, the surface of the walls therefore has a roughness, and the dimension of the roughness is of course length. So we can go ahead and make it dimensionless by dividing it by D. And this friction factor, Darcy friction factor, is also a function of the duct shape. So now the question is how to find F, the Darcy friction factor, because we don't need it in order to be able to calculate HF from this equation, which is called Darcy-Weisbach equation. So that's the goal now that we will see in the next slides, and the goal is to find an expression for F, the Darcy friction factor in a pipe. All right, so in the previous slide, we got to this point. So we showed that HF, the head loss, is found by this empirical equation, FL over dV squared over 2G. And also we showed that F is related to the shear stress on the wall of the pipe. Now we need to go back to our laminar fully developed pipe flow. We did solve this problem in chapter 4. We found an analytical solution for the velocity profile in this form, parabolic velocity profile for laminar flow in a pipe. If you recall from the previous chapters, where U max here is given in terms of the radius, viscosity, and in this case minus dp dx. If in the case of a horizontal pipe, then minus dp dx is simply equal to delta p over L. But in the case of an inclined pipe, which is the case here, the most general case, minus dp dx has another component because of a change in the elevation between 0.1 and 0.2. So it's going to be shown as dp over L plus rho g delta z over L. And also from the previous chapters, we showed that the average velocity v is half of the maximum velocity at the center line. And we've also found Q, the volume flow rate, the integral of the integral of the flow rate over the entire area of the pipe. And also we found tau, the shear stress on the surface. So tau is simply equal to mu du dr on the surface of the pipe, which is R equal to capital R. And we show that it's equal to 4 mu over V over divided by R. Okay, so this is what we need, tau equal to 4 mu V divided by R. Now if we substitute tau W from this equation shown in the circle back in the equation that we developed before, and use also the definition of using the Darcy-Weisbach equation, the one on the top, this one. Then we can go ahead and find HF, the head loss, as a function of the viscosity of the fluid, the length of that pipe section, velocity, average velocity V, rho G d square. If we want to show it in terms of Q, the volume flow rate, we can convert V to Q by the equation V equal to Q divided by the cross-sectional area, pi r squared. Okay, so this, what we see from this equation, the head loss is inversely proportional to the pipe diameter to the power of 4. So from the second equation here, if Q is constant, so if the size of the pipe is doubled, like is 1 inch becomes 2 inches with the same flow rate, the head loss will decrease by a factor of 16 for a given Q. So a reduced head loss means a reduced pump power at the expense of a larger tube. It's heavier, more expensive, capital cost, infrastructure, mounting, and so on. So there should be a compromise between the pumping power and also the cost and weight of the pipings. So essentially, the narrower the pipe, the higher the friction loss, because you see HF is inversely proportional to the diameter to the power of 4. So it's a very strong dependence. All right, so we can also go ahead and show the friction factor F. So we said that friction factor is equal to this equation related to tau. This is what we obtained before. Now if we substitute tau from this equation and so replace it by 4 mu V over R, put it here and simplify, we will generate the Reynolds number. And we will see that the friction factor, the Darcy friction factor, is actually equal to 64 divided by Reynolds number determined based on characteristic length D, the diameter of the pipe. So this is a very famous and useful equation. Friction factor, Darcy friction factor for laminar flow is equal to 64 divided by Reynolds number. So you see that in this case for laminar flow, the roughness of the tube does not have an effect, because laminar flow actually covers up the rough area. So for a laminar flow, friction factor is a function of Reynolds number only. But this is not the case for a turbulent flow. For a turbulent flow, the friction, the roughness also affects the friction. But for a laminar flow, it's simply 64 divided by Reynolds number. And as the Reynolds number increases, so as the Reynolds number increases in the range of laminar flow, the Darcy friction factor decreases. So for a very low Reynolds number flow, which is the creeping flow or Stokes flow, the friction factor is very high because viscosity is dominant. So the pumping power will increase as the Reynolds number decreases. All right, so now let's go ahead and do 2 questions. So far we have found the head loss for a laminar flow, not turbulent flow yet, that will come next. So this is problem 625 of the book. For the configuration shown in the figure, the fluid is ethyl alcohol at 20 degrees C. So we do know the properties, we can go ahead and look up the properties. And the tanks are very wide. So that means that The velocities on the surface of the tanks is negligible. That's the meaning of the tanks are very wide. Find the flow rate that occurs in cubic meter per hour is the flow laminar. So the equations that we have developed so far are only good for laminar flow. So we need to double check that the flow is actually laminar. Okay, so in order to find the flow rate in the pipes, based on the configuration that we see, we can go ahead and write the energy equation or the modified Bernoulli's equation. So between, let's say, we choose point 1 here on the surface of the upper tank and choose the point 2 here on the surface of the lower tank, or we can also choose point 2 at the exit of the pipe down here. So it's the same, the answer would be the same if we choose point 2 on the surface or at the bottom of the pipe, because these are interrelated anyway. So the modified energy, the energy equation, the pressure term, velocity term, elevation at point 1. This is point 1 here, and then point 2 here. And then we need to the right side of it, we need to add the energy loss, the head loss. So everything here is in terms of head. The unit of all of these terms is unit of length, meter. So we do have HF. So in the previous, like in chapter 4, when we introduced the energy equation, we did have something like this. However, in that chapter, HF was simply given because we didn't know how to calculate it. So it was given. But here, at least for laminar flow, we do know how to calculate it just with the derived equations in the previous slides. So now here we actually have to calculate HF. So given that pressure is atmospheric pressure on the surfaces of the tanks, and also given that the surface of the tanks is very wide, so these velocities are negligible. So the pressure term negligible, the velocity negligible. So the pressure there, this atmospheric pressure, so it cancels out. Velocities are negligible. So we end up only with a difference in Z and HF, the friction factor. So we see that the head loss due to friction. So HF is therefore balanced by the change in the elevation. Here there is no pump, right? So there is no pump in the system. So this head loss has to be made up by something, right? So that something is the elevation. So in other words, the potential energy plays the role of a pump. So HF is therefore equal to delta Z. And if we look at the problem here, delta Z is 40 centimeter plus 50 centimeter, 90 centimeter. So we put it here and put it equal to HF. But from the previous slides, we just showed that HF is related to, for a laminar flow in a pipe, is related to the volume flow rate using this equation, and also the diameter of the pipe, length of the pipe, viscosity of the fluid, and density of the fluid. For ethanol, the properties are given, we just plug in, everything's known except for Q. Oh, by the way, I should mention that here the length of the pipe, the length of the pipe is the entire length from this point all the way down to here. So that would be the length of the tube that we need to use. So inside the pipe, inside the tank, there is no pipe, so this length is not considered. So we do have head loss only when the fluid flows through the pipe. all the way to the bottom. That's why I said that for point 2, you could either choose the surface or the bottom or the end of this pipe. So for the length of the pipe, we actually do need to consider uh, the length, the entire length of the pipe, which is uh, 80 centimeter here, and then another 40 centimeter between the two tanks. So length of the pipe is 1.2 meters that we have here. So if we go ahead and calculate Q, so that's Q in cubic meter per second, and then if you want to show it in cubic meter per hour divided by multiply it, if we want to show it in cubic meter per hour, then multiply this by 3600. So that would be the heat flow, the volume flow rate. Now we need to double check to make sure that this flow is actually laminar. So for this purpose, we will need to calculate the Reynolds number. So Reynolds number is rho v d over mu, but v is equal to q divided by pi d squared over 4. So we can calculate the Reynolds number, which is equal to 795. It's less than 2100 or 2300. The threshold between laminar and turbulent, 2300. So yes, so we do have laminar flow. As a result, our analysis here has been correct. All right, so let's do problem 621 of the book. And we want to practice another problem, assuming that we do have laminar flow. For this purpose, we consider a small house, a tiny land houses, which are only 30 centimeter height. So let's assume that, that's, the case. So in order to have laminar flow, we do need to have a very narrow tube diameter, short tube diameter. In this case, the diameter of the drain pipe is 2 millimeters only, and we assume that when the gutter is full, so it's full of water, and the diameter is 2 millimeters, the length is 20 centimeters. We want to find what is the rate of draining. First part of the problem. So we want to find the rate of the draining. So for this purpose, we do need to find the velocity in the pipe, or directly we need to find the volume flow rate in the pipe. So okay, so first let's assume that the flow is laminar. We don't know yet for sure, but first let's assume that it's laminar, and actually the problem states that the rainfall is laminar, but later we need to go ahead and verify that. And the reason that the height of the house is only like 30 centimeter is because we want to actually create a problem for laminar flow condition to test our equations that we just derived in the previous slides. So for this purpose, let's write the energy equation between here, the surface of the gutter, and also the exit of the tube. So 1 here and 2 here. So on the top surface, the pressure is atmospheric. At the surface 2, at the bottom, the pressure is atmospheric. So pressure terms cancel out. On the top, like the velocity can be neglected because the surface of the gutter, it's connected to the roof, right? So we can assume that the velocity of the water up there is actually very small. But the velocity at the exit of the drain tube is not negligible. So we do have a velocity down here. Okay, and there is an elevation. So if we write the energy equation, we end up with this equation, delta is equal to V squared over 2G plus HF. So in other words, on side one, so for point 1, we have Z1, this is point 1, and this is point 2 here. So on the left side, we have Z1, and then the pressure term, the velocity term, the pressure term cancels out with the pressure term on the right side. On the right side, we do have Z2, which is 0, and we do have velocity, and we do have a head loss. A head loss is due to the flow inside this pipe. But from the previous slides, we found head loss for laminar flow equal to 64 divided by Reynolds number. We can show it that way in terms of Reynolds number, because in the Reynolds number we do have velocity, which is unknown, everything else is known, or we can directly show HF in terms of the values. If we want to use the equation that we had, F the friction factor was equal to 64 divided by Reynolds number, and then we would need to use the Darcy-Weisbach equation in order to generate or create all terms for head loss HF laminar. But this equation directly gives us what we need for the energy equation. I hope that it's clear, so let me explain again. So in order to find HF, oftentimes people cannot remember the equation like this, but people can remember that HF from Darcy-Weisbach, HF is equal to F, the Darcy friction factor, times L over D times V squared divided by 2G. And for laminar flow, F, the Darcy friction factor, is equal to 64 divided by Reynolds number. So if we combine those two, we will end up with this equation. If you do have a formula sheet in the exam, you should have directly this equation to save time. Okay, so for water, density is given, viscosity given, and delta Z here is 20 centimeters, 0.2 meter. If you plug in this equation for the knowns, so the left side delta Z is known, here you do have a V squared. In HF, you will generate a velocity to the power of 1. So you will end up with a quadratic equation. So Z equal to V squared here. On the other side, everything else is known except the velocity. So you will generate an equation like this, a quadratic equation, and the solution to this equation is given here from algebra. So we can go ahead and find the velocity. We only accept the positive answer of this equation. So velocity is given as 0.945 meter per second. Now if we multiply by the cross-sectional area of the pipe, P pi d square over 4, then we can get the flow rate in cubic meter per second. If you multiply it by the number of seconds in 1 hour, you will get it in cubic meter per hour. So that's therefore the velocity of the fluid in the pipe. It's assuming that it's laminar flow, we need to double check that, and also the volume flow rate. Problem has another part. If the gutter is designed for a sudden rainstorm of up to 5 millimeter per hour. So let's say there is nothing, all of a sudden a rainstorm occurs with a rate of 5 millimeter per hour. So 5 millimeter per hour. So for this condition, what is the maximum roof area that can be drained successfully? So it's like the roof area is unknown, but we do have the rate of rainfall, which is 5 millimeter per hour. So it means that if we want to find the area, therefore, if we divide the volume flow rate that we found, divided by the rate of the rainfall, we will get the maximum surface area that can be uh, actually drained using just one of these pipes. So 2.14 cubic meter. And finally, to make sure that actually our analysis is correct, we calculate Reynolds number, rho VD over mu, and C that is equal to 1890. It's less than 2300. Therefore, the flow is laminar. So we were actually allowed to use this equation for HF. For Reynolds number higher than 2300, HF could not be obtained from this analytical solution. So you may ask that, okay, so what to do for the case of Reynolds numbers larger than 2300? That will be the subject of the following lectures. So up to this point, we finished the analysis of laminar flow in tubes and pipes. So in the next section, we will start to talk about turbulent flow and then see what will happen, how to calculate the head loss in the case of a turbulent flow. All right, thank you for your attention.